The question is, why is the light of an electric bulb white? Have you ever wondered why the coiled wire inside a common electric bulb is not red, not blue? It illuminates our homes with exactly white light? The answer lies much deeper, hidden in a fundamental law of quantum physics. And on this journey, Planck's radiation law and the temperature of matter will accompany us. Let's explain the matter step by step. Step 1. When you press the switch, electric current flows through the tungsten filament inside the bulb. The melting point of tungsten is about 3,422 degrees Celsius. That is about 3,695 Kelvin. When a high current flows through it, the filament becomes extremely hot. The temperature reaches about 2,500 degrees Celsius to 3,000 degrees Celsius. That is 2,773 Kelvin to 3,273 Kelvin. Now the question is, why does an object emit light when it is hot? Step 2. A fundamental truth of physics is that any object with a temperature above absolute zero, minus 273.15 degrees Celsius, emits electromagnetic radiation. The wavelength of this radiation depends on the object's temperature. As an object is heated, the color of the radiation it emits changes. Around 800 Kelvin, 527 degrees Celsius, reddish. Around 2000 Kelvin, 1727 degrees Celsius, orange. Around 3000 Kelvin, 2727 degrees Celsius, orange-white. Around 5200 Kelvin, 4927 degrees Celsius, white. The temperature of the filament in our light bulb is around 2800 Kelvin, so it gives off a white glow, although it has a slight yellowish tinge. Step 3. Planck's radiation law explains how much light an object will emit and at what wavelengths. The relationship between the intensity and wavelength of radiation emitted by an ideal black body, the filament of our light bulb, behaves almost like an ideal blackbody. At a temperature of 2800 Kelvin, the radiation emitted according to this formula spans the entire visible spectrum from red, 700 nanometers, to blue, 400 nanometers. When all colors are seen together, the brain identifies it as white. Step 4. Wien's law states that the wavelength, lambda max, at which light is emitted from a black body with maximum intensity is inversely proportional to the temperature, T, of the object. Lambda max equals B over T, where B is Wien's constant, which is approximately 2.9 times 10 to the minus 3 meters Kelvin. The temperature of our light bulb filament is T equals 2800 Kelvin. Then lambda max equals 2.9 times 10 to the minus 3 over 2800 is approximately 1.035 times 10 to the minus 6 meters equals 1035 nanometers. This value is in the infrared region, outside the visible spectrum, which explains why the bulb produces so much heat, not light. If the temperature of the filament could be increased further, the value of lambda max would decrease and shift towards the blue end of the visible spectrum, and the light would appear whiter or bluish. Step 5. The human eye has 3 types of cone cells, sensitive to red, green, and blue light. When all 3 wavelengths, red, green, and blue, hit our retinas from a light bulb, the brain processes these signals together and interprets them as the color white. The white light from a typical electric bulb is actually thermal radiation from a tungsten filament heated to 2800 Kelvin. According to Planck's law, the radiation emitted at this temperature contains all the colors of the visible spectrum, and our brain identifies that mixture as white. But the interesting thing is that most of this light is infrared, so the bulb produces not only light, but also a lot of heat. So the next time you see a light bulb turn on, remember, you're actually looking at a piece of a star at 2800 Kelvin, illuminating your home according to the laws of quantum physics. If you like the video, please like the video and subscribe to the channel. Thank you.